Okay friends, so we now start with our next another method of constructing interpolation function, because interpolation function is the core thing which defines the definition or design of finite elements. Different elements, they are characterized by the interpolation function or shape function as they are called. So, we discussed one method of PC inverse for constructing interpolation function for triangular geometries. That is a very general technique. It can be applied for any finite element approximation, as long as the coordinate matrix C matrix is invertible. In practice, in theory they should be, it should always be invertible, but in practice there may be some problem because of some meshing constraint. We may have one particular element, for example an element may be very skewed element like this, right. So, if this is the skewed element, then the coefficient matrix may be ill conditioned, because there is not much of a difference between this line and this line, they are very close by, and the similar, and because of that the rows and columns of the C matrix may not be very independent, and within the, because in on digital computers we are also looking at the possibility of errors due to round off, and that may incur this kind of skewed elements may incur very high round off error, and the matrix may be singular maybe or near singular, and once it is near singular then computation of inverse becomes highly error prone, and therefore, this PC inverse, although in principle it should work, that is rarely used in practice. So, we look for another way of constructing elements. So, C0 continuous elements, we already 3 noded element we already saw. Then next in line is the quadratic element, which is complete up to second degree quadratic, second degree terms. So, that those involve 6 terms, that is constant term, linear term in x, linear term in y, x square, x y and y square. So, together 6 coefficients, right. So, these 6 coefficients would be defined by 6 nodes of the 6 noded triangle. So, 3 vertices and 3 mid side nodes. Next in line, if we wish to have cubic variation of the primary variable within the element domain, then I need to add 4 more terms, that is x cube, x square y, x y square and then y cube. So, 4 more terms to 6 terms that are already there. So, to total 10 coefficients, total 10 terms in polynomial approximation. So, those 10 coefficients can be uniquely mapped to the nodal variables by having 10 node element, and out of those 10 node 9 are on the sides of the element and 1 is in the interior of the element domain, right. So, that is what the geometry defines these 3 noded triangular family. So, quadratic polynomial approximation for primary variable can be achieved with 6 node triangular elements defined by 3 vertices and 3 mid side nodes, and then the 6 nodes for interpolation provide 6 constraints for evaluating coefficients of the polynomial approximation, just as we did that PC inverse 6 nodes coordinates, and we can define unique mapping between the nodal coordinates and the interpolation function for that node, defining the satisfying the interpolation criteria n I x j y j is equal to delta I j. So, in general, for a triangular element, the total number of nodes required for a polynomial approximation of degree p is given by node n d is the number of nodes required. So, p plus 1 multiplied by p plus 2 by 2. So, that is the total number of nodes that are required if the idea is to construct polynomial approximation that is complete up to pth degree, right. So, that is just the number of nodes that will be required for defining the approximation of desired degree. One thing is what is required, what needs to be paid attention to is triangular family is such that there is always perfect match. If it is a 3 noded triangle, it is complete up to first degree. There is no spurious term, no term from the 1 or 2 terms of second degree or third degree extra terms, right. If I go for quadratic element, then there are 6 nodes in the triangle and they will completely define the second degree variation, quadratic variation. Similarly, the 10 node triangle would completely define the 10 node the third degree polynomial approximation, cubic polynomial approximation. There would not be any extra term, spurious term from 4th degree or 5th degree in the approximation. So, that is a unique feature of triangular finite elements that should be mentioned. So, I told you about mentioned a little while in the previous lecture about the possibility of coming up with another way of constructing or defining interpolation functions. We can look at these interpolation functions, that is how they were first defined. Unfortunately, this analogy does not carry through as well in the higher order elements. Nevertheless, it is very interesting to note the correspondence. So, this point P, let us say in the interior of the element, any point P, let us say its coordinate x and y. So, this point P is defined, I mean I can always define this point P by the way it divides this triangle into 3 different areas, is not it. So, A1 is the area covered by this point P and other 2 vertices other than node 1. Similarly, A2 is the area defined by point P and the vertices other than node 2. So, P31 is the area covered represented by A2, and similarly P12 is the area represented by A3. So, that is what we assign it to node 3. So, this is similar to the way we label the sides of a triangle. The side opposite to the vertex is referred to that side. So, this one would be side 3, this one would be side 1 and this one would be side 2 for this particular triangle defined by vertices 1, 2 and 3. So, in similar fashion. So, now I define the normalized area. So, define point P, any point P x y defines divides this area of the triangle, let us call it delta, into 3 different areas A1, A2, A3. Now, I define the ratio of A1 these areas with total area of the triangle. So, define L1 as A1 divided by delta, L2 as A2 divided by delta and L3 as A3 divided by delta, the area of the triangle delta. Now, interesting thing is L1 plus L2 plus L3 is equal to unity, and this is a unique specification for the point P x y. Wherever I take this point P, these ratios will move accordingly, will change accordingly. So, these ratios in a way serve as coordinates of the point P, right. So, instead of x and y, I can locate the coordinates, I can locate any interior point by talking in terms of these ratios of the areas. So, the vertices are defined accordingly. So, vertices are defined, let us say vertex 1 So, if I have this vertex 1, so point P comes coincides with vertex 1. So, the entire area is A 1, right. So, L 1 is going to be 1, L 2 is going to be 0 because A 2 is 0 and A 3 is 0. So, coordinates of vertex 1 will be 1 0 0, coordinates of vertex 2 will be 0 1 0 because L 2 will be 1 in the case of vertex 2, point P coinciding with vertex 2, and in case of point P coinciding with vertex 3, node 3, the coordinate of vertex 3 will be 0 0 1. So, that is the basic definition, and that is the limit. The L 1, L 2, L 3 they can vary between 0 and 1. 0 is the minimum and 1 is the maximum. So, that is important thing. Now, we take this concept forward, that this L 1, L 2, L 3 these are what I call as local coordinates. Local coordinates imply that they are defined only within the interior of this element. They are local to this particular element that we are looking at, right. So, they are not influencing any other element, or they are not these values do not affect any other element or outside this particular domain that we are looking at, defined by 1, 2, 3. So, I define this by using this area coordinates or local coordinates L 1, L 2, L 3, it is possible to construct interpolation functions of Lagrangian form. Lagrangian form, they, if you recall, they just multiply the equations of line, or if you look at it, Lagrangian interpolation is just for any node I sorry, this would be j. So, x minus x j divided by x I minus x j, right, and I is not equal to j, as long as I is not equal to j. So, this automatically satisfies, this is going to be equal to unity when it is evaluated at x I, and it is going to vanish at all other nodes j, right. So, n minus 1 number of nodes it is going to vanish, and at only one node it will evaluate to unity, and that is node I. So, this is how the Lagrangian interpolation formula works, and this can be very easily used to define the interpolation for triangular geometries using these local coordinates L, L1, L2 and L3. We will see how. And local coordinates are also known as natural coordinates in some texts. So, a more general interpretation other than this area is, as I said, we look at it as value ranging from 0 to 1. So, L1, let us look at L1. So, L1 is 0 along this edge, is not it. So, node 2, for node 2 L1 is 0, for node 3 L1 is 0. So, this is the line for L1 being 0, and for node 1 L1 is 1. So, this L1 is the line, the coordinate line parallel to this edge 2 3, and it goes from 1 0 at the edge 2 3 to 1 at the line passing through node 1, parallel line passing through node 1, and in between it varies linearly, it is interpolated linearly. So, from 0 to 1 here L1, and similarly for L2 it goes from 0 at node the line 1 3 and unity at node 2. So, it goes from 0 to 1 along this in this direction parallel to this edge 1 3, and similarly for L 3 it is 0 at edge 1 2 and goes to unity at node 3, and the L 3 value varies from 0 to 1 in this direction, right. So, now it becomes very simple. Every point will be intersection of these 3 grid lines L 1, L 2, L 3, all varying from 0 to 1, and wherever whatever the intersection happens, that becomes the coordinate of that particular point. So, the nodes in this case 6 node triangle, the mid side nodes, they all refer to L 1 being equal to, I mean this line 6 4, that is midway between node 1 and this 2 3, right. So, L 1 is equal to half here along this line, and similarly 6 5. So, node 6 and node 5, that line is L 3 corresponds to L 3 is equal to half, and this line 4 5 that corresponds to L 2 is equal to half, because L 2 is equal to 0 here and L 2 is equal to 1 here, and it is half along this line, right. So, that way we can we have these values, and if I going by the Lagrange interpolation, all that I need to know, for example, let us look at this constant strain triangle 3 node, then interpolation function for node 1 has to be 0 at node 2 and node 3. So, I just say interpolation function for node 1 is simply L 1, because L 1 is 0, right. So, L 1 is the interpolation function for node 1 for 3 noded triangle. Similarly, L 2 becomes the interpolation function for node 2, and L 3 becomes the interpolation function for node 3 for 3 noded triangle, constant strain triangle. And if we work out these expression, we will find that they work out exactly identical expressions as we derived earlier using the method of polynomial approximation and calculating the inverse and enforcing the interpolation criteria. So, similarly, so we can define that, work out this expression, and we can verify, and the centroid of the triangle is defined by the area coordinates or local coordinates L 1, L 2, L 3, they are all 1/3, right. So, this is the area coordinate, I mean what is this local coordinate for 3 noded triangle. So, this is the area represented by point P x y. So, the field variable within for the primary variable within CST constant strain triangle can be given as L I u I, sigma L I u I. So, that is L 1 u 1 plus L 2 u 2 plus L 3 u 3 is equal to the variation of primary variable u within the element omega e, right. So, the interpolation functions for higher order elements can be expressed in the Lagrange form in terms of the local coordinates of the nodes. How do we do that? It is very simple actually. We look at it again, go back to these equations. So, let us say this node 4 mid side node. So, mid side node, so interpolation function for node 4 requires that it has to vanish at all other nodes. So, that means it has to vanish at this particular edge and it has to vanish at this particular edge. So, node 4 I can get the interpolation function for node 4 satisfying that criteria by just multiplying L 1 with L 2. L 1 and L 2, L 1 vanishes along this line and L 2 vanishes along this line, right. So, if I multiply L 1 and L 2, I satisfy the criteria what is the value L 1 and L 2 along this line. So, it will always be 0. Now, I come to the third criteria, that it has to be equal to unity when evaluated at node 4. So, what is the value of L 1 and L 2 at node 4? So, L 1 is equal to half at node 4, L 2 is equal to half at node 4. So, I evaluate what is the value going to be L 1 L 2 at node 4, it works out to 1/4. So, I just multiply it by 4. So, N 4 becomes equal to 4 times L 1 and L 2, and that is what we have here. N 4 is 4 times L 1 and L 2. Similarly, for other mid side node N 5, it will be equal to 4 times L 2 and L 3, because N node 5 is between the nodes 2 and 3, right. So, that will be the interpolation between that will be line where L 1 is 0 and L 2 and L 3 will be 0 along other two edges. So, that is what we multiply L 2 and L 3 and evaluate it to evaluate this product L 2 L 3 at node 5, which works out to evaluates to 1/4, and therefore, we scale it by 4 to get unity at N 5 at the node 5. And similarly, for node 6 we have by similar arguments we have the interpolation function as 4 times L 3 and L 1. And similarly, this one we can work out similar arguments for N 1 and N 2. So, for node 1, obviously, it has to vanish at this particular edge. So, it is equal to L 1. So, L 1 vanishes at this node. So, this is fine, this line. So, all these 3 nodes are taken care of vanishing condition. At this particular value, the equation of this line is L 1 is equal to half, right. So, or in other words, I just say it will be equal to twice L 1 minus 1 is equal to 0, right. So, L 1 minus half is equal to 0 or twice L 1 minus 1 is equal to 0. So, I just multiply these two equations. So, equation of this line and equation of this line and evaluate it at node 1, divide by that number. So, when I evaluate it at node 1, what do I get? So, L 1 multiplied by twice L 1 minus 1. So, if it I evaluate it at node 1, so at node 1 L 1 is equal to 1. So, at node 1 it is one multiplied by 2 minus 1 is equal to 1. So, this is already satisfied, and this obviously varies vanishes at other two lines. And similarly, we have the similar expressions for other nodes. So, N 2 is equal to L 2 multiplied by twice L 2 minus 1, N 3 is equal to L 3 multiplied by twice L 3 minus 1. So, that is a simple Lagrange's form of interpolation function. So, no complicated analysis or computation of derivative or inversion of large coefficient matrices. L 1, L 2, L 3, the moment if we define L 1 and L 2, L 1, L 2 and L 3 for 3 node triangle vertex, and then we can by using these values of L 1, L 2, L 3, we can actually define the entire set of interpolation functions for higher order elements and 3 including 3 noded triangle. So, 6 node triangular elements are very easily given like this. So, they are quadratic second degree polynomials, as you can see. Each of these terms, L 1 is first degree polynomial, this is also first degree polynomial, product of them gives you second degree polynomial. So, next is the issue of computation of domain integrals. So, eventually all the after all that we do, we need to eventually evaluate the integrals of this form, is not it. So, we need to evaluate these boundary integrals for each element. So, W 1 will be replaced by one of these interpolation functions n I, n j, n k, whatever. So, these type of expressions have to be evaluated, and once we do this, so u hat will be again interpolation polynomial, interpolation approximation. So, combination of n I, n j, n k linear combination, and this expression will be also based on n I, n j, n k. So, there will be essentially the integrand is going to be polynomial. What we are trying to integrate here is a polynomial of different orders, right. So, the terms would involve different orders of x raised to the power m, y raised to the power n integrated over some domain, triangular domain over dx dy. So, let us call this as an integral m n, generic integral. Now, this for triangular domains there are analytical expressions already available based on what are the powers m and n. So, some of the commonly used integrals that we will need, that we may need in this case of finite element approximation for triangular domains. So, I 0 0, so 0th order, so constant interval, so that is only the triangle area of the triangle, first power of x and 0th power of y. So, that is just x hat, that is the x coordinate of the centroid, and similarly I 0 1, that is area of the triangle multiplied by evaluated at the centroid. So, y hat is the coordinate of the y coordinate of the centroid, and similarly for 1 1 for the product x y. So, we have similar expression summation over all three vertices and then product of the coordinates of centroid, then 2 0 x square term, then y square term, etc. And there are other higher order terms as well, which can serve the purpose and which can be used analytical evaluation of the integrand, and that will facilitate the complete evaluation of the integrand. And the only thing that now remains is the boundary term, how to evaluate the boundary term, and that is what we will discuss in our next lecture. Thank you.